This section, we're gonna try to gather everything we discussed in the first part and in the second part into something more meaningful. And this chapter will be an introduction to the next week discussions. So bear with me here because this chapter will be a link between what we discussed so far and what we're gonna see next week. So in this chapter, we're going to try to make what we call it an inference based on a single sample. So as a simple example, um, suppose you're interested in the average amount of money that students in this class have in their pocket. How, how would you find out? If I want to know how much money in your pocket, my pocket, and everybody in this class, and I would like to make an assumption on, for example, the average of the amount we totally have, or what range overall we totally have. So to do so, let's take a step back. So if you remember last week, we said that we have statistical methods. Those statistical methods are divided into descriptive statistics and inferential statistics. Last week, we covered the descriptive statistics when we discussed mean, median, mode, standard deviation, different type of charts, etc., etc., etc. That all fall under descriptive statistics. What we will discuss from now on is on the inferential statistic part. Inferential statistics itself divided into two different topics: estimation and hypothesis testing. Estimation and hypothesis testing. We will start with estimation. Estimation itself, it's also break down into two different ideas: point estimate and interval estimate. All right. I hope the breakdown is clear because we're gonna move from one topic to another. Statistical method, we have inferential and descriptive. We're done with the descriptive so far. We're moving to the inferential. Inferential has two topics: estimation, hypothesis testing. We will start with the estimation, which also has two topics: the point estimate and the interval estimation. Before we start talking about estimation in general, we need to understand something, which is the target parameter. As we discussed in the second part, the main idea of having a sample and making statistical tests on the sample is to estimate the population parameters, or what they call it here, target parameter. So I'm taking a sample of people income to know the entire American population average income. So my target parameter is the average income of the American citizen by taking a sample of people. My target parameter is to find the average of students' grades in the past 5 years who study with us by taking a sample of the students in this class, calculating the mean of this sample to find or estimate the target parameter, which is the entire population mean. When it comes to your own research, when you're trying to conduct your own research and you want to identify between quantitative and qualitative, usually when you use the words like mean, average, that's more related to quantitative. When you use words or keywords like proportion, percentage, rate, chances, that's more related to qualitative research. That's in general when we're talking about target parameter. Now, remember we said that estimation broke down into point estimate, and interval estimate. Point estimate is basically we are trying to say that we are, how do I say it? We are trying to do, what we are trying to do is by using the sample we have, we are trying to estimate an exact single point of the population parameter. So the wording will be, when I'm trying to do a point estimate, is to saying that the student average grade, the student average grade is exactly equal to 75%. The average income of the American citizen is exactly $50,000 a year, and so on. So by point estimate, we are using the data we have in the sample to test, to check, to make sure that the population parameter is equal to a specific point or a specific value. So that's the point estimate. On the other hand, the interval estimator, we are not trying to specify a specific point. We are trying to specify a range. So instead of saying that the student's average grade is exactly 75%, I would say the student's average grade is between 70 and 80. Instead of saying that the average American income is $50,000 a year, I would say the average the average income of American citizen is lie between 45,000 a year and 55,000 a year. So that's the main difference. In a point estimate, you are trying to test if the parameter of the population equal to a specific value. In the interval estimator, you are trying to check if the population parameter or the target parameter is fall within certain interval. This is the main difference. I hope it's clear. So when you are trying to do the interval estimation, you are trying to build a range. This range, okay, let's go back a little bit. This range usually have an upper limit and lower limit, upper limit and a lower limit. And there's a third component, which is the confidence level. So when I'm saying the average student's grade is between 70 and 80, you should add how much are you sure that this is correct. So I would say, like, there is 90% chance, or I'm 90% sure, or I'm 90% confident that the student's grades fall between 70 and 80. 80% confidence, or 80% sure, or 80% confidence that the American the average of the Americans, the average income of the American citizen is between 45,000 and 55,000. So for interval estimation, there's three major things that you have to think about: the minimum, average, the lower limit, the upper limit, and the confidence level. So the confidence level, this is just to simplify what we're trying to say. So I have the population. This yellow thingy is the entire population. I took a sample, and I calculate the sample of I calculate the X bar, or the mean of this sample, and I found it's 50. Based on this result, I will say I am 95% confident that mu, or the population mean, is between 40 and 60. So this is, in general, the way we're trying to do estimation, or building estimation, or an inferential estimation. This chart here will summarize what we're trying to say. So this line here represents the thick black line, represent all the values that within the population. What we are trying to do is to take a sample and find a value. If we are trying to do a point estimate, we are specifying that the population parameter is equal to this point. But if we're trying to build a confidence interval, we will say that the population parameter lie between the lower limit and the upper limit. So this is the difference between the point estimate and the confidence interval. I hope it's clear. In real life, I would say the majority of our tests in businesses like about more interval. Like it's very rare to try to use a point estimate, like exact amount or exact point. What we mostly try to build or check or to test if a certain value fall within certain range that makes sense to us. So how do we do that? How can we calculate the lower limit or the upper limit, and what do we do with the confidence level? First, let's discuss what we call the confidence coefficient or the confidence level. It's very much telling me or a number or a percentage or a probability that tell me how sure or how sure you are with the results you're getting, or how much do you trust that the results you have are correct. So if we try to merge what we're discussing here with what we learned in the first um, session, the first part of today's session, I will have this uh, standard normal distribution shape, this line. Then I put the middle line, which is 0. Now, the question is, if the population parameter fall within this range to this range with confidence of 95%. So technically, what you are trying to say is this line here hold underneath it 1, which is 100% of the possibilities. 95% will be from the middle to the right and from the middle to the left. That will leave 5% only that the estimation you have is wrong. This 5% could be on the either side, the left or the right. So that's why we divide this 5% into 2.5 to the left, 2.5 to the right, or what we call it alpha by 2 here and alpha by 2 here. Alpha is this 5% remaining, which is the chance that your calculation is wrong, or the chance that the calculation is mistaken, or the chance that the parameter you're trying to estimate is out of the range you're trying to build. With that being said, by looking to this chart here, the line hold 100% of the possibilities, or 1. This part in the middle represents the 95% confidence I'm trying to build. Those green area represent the possibility that I'm wrong, my calculation is mistaken, or the parameter is out of the range I'm trying to estimate. So what left is to find this upper limit and this lower limit. That's the only thing left, because right now we know the confidence level is 95%. Remember, when we're trying to estimate something or estimate a range, we need upper limit, lower limit, and confidence level. Confidence level is what we're discussing here. 95% an example. Could be 90, could be 80, could be any number. For my example here is 95%. That means there's still 5% chance I'm wrong. This 5% chance could be to the left or to the right, meaning the parameter could be higher than the upper limit I have, or could be lower than the lower limit I have. which represented by those two greens area. This 5% is divided into two sections, 2.5% to the right, 2.5% to the left. This covers the confidence level. What I need to know now is what is the upper limit and what is the lower limit. And to find that, we use this formula here. You take the X bar, which is the mean of the sample you have, plus the Z value based on A on 2. So you go to the Z table, you check what is Z when it's 2.5, as we saw in the first section, and you multiply the Z value by the standard deviation of the sample. And this will give you the upper limit. The lower limit will be X bar, which is the sample mean, minus Z value multiplied by the standard deviation of the sample. That will give you the upper and the lower limit. Then we have the full picture. The parameter is fall within the upper limit, which is X bar plus Z multiplied by standard deviation, and the lower limit, which is X bar minus Z multiplied by standard deviation. And I'm 95% confident that the parameter of, or the population mean, or the parameter of the population fall within those two ranges. This is very much what we discussed so far. Let's look for an example. Here in your example here, we check 100. We are in like a wine factory or Coca-Cola factory, whatever example you decide, but we are selling some kind of drink, and this drink is supposed to have 2 liters of liquid inside it. We took a sample of 100 bottles to check if we actually have 2 liters in every one of these 100 bottles. We assuming that we might have a 0.05 difference in the bottle. When we check the 100 bottle we found, we took as a sample, we calculate the average of the liquid inside these bottles. We found that the average is equal to 1.99. So meaning the average liquid in the bottles is equal to 1 liter 0.99. It's not 2 liters. So the question is, using confidence level 90%, meaning that you are 90% sure that the amount of liquid inside this bottle is equal to 2 liters. Now we are using the sample mean to estimate a population mean, or to test the population mean. We are trying to test if the mean of the population, or mu, is equal to 2 liters. This is a point estimate. It's not an interval. We're trying to test a specific point of so to do so, we said we are trying to estimate mu. Where is mu? So as we say, the lower limit will be X bar minus Z alpha by 2 and standard deviation of the sample. And the upper limit is X bar plus Z multiplied by the standard deviation of the sample. Our X bar, as we saw in the example, is 1.99. This is our X bar. Z alpha by 2, our alpha here is 10%, meaning we have, okay, we said the confidence level is 90%. That means we have a 10% alpha. That means 10% we might be wrong. This 10% could be 5% in the left and 5% on the right. So what you will do is you will go to the Z table and check for the value of Z when you have 0.5, and that will give you a Z equal to 1.645. Standard deviation is given by here 0.05 divided by the square root of the sample, which is we took a sample of 100 barrels. That will give me the lower limit. Same thing for the upper limit, x bar plus z value, which is equal to the one on the left, multiplied by the standard deviation divided by the sample, the square root of the sample. Now, after doing the calculation for the left and the right side, I found out that the mu, or the average amount of liquid in the entire population, or the entire production I have in my factory, will be between 1 liter 0.982 and 1 liter between 998. That means my advertisement here that this bottle has 2 liters is false. I have a problem in my production line because the average amount of liquid inside the bottle is less than 2 liters, which I'm trying to test here. So that's an example of what we discussed above. Is it clear? Any question? All right.
So far, everything is good, but I think we need one more example on this confidence interval.
I think this is the only example we have. Oh no, there's another one, but that for a different type of statistics, but the same idea. Now, let me go back a little bit. Yeah, let me go back a little bit here to this slide, which I intentionally skipped to go right to the example. So everything we discussed so far assume two conditions. The first condition is we have a random sample. If your sample is not random, it's biased, we can do any of these tests. Everything will be wrong. So it should be a random sample. That's number one. Number two, using Z to calculate the upper limit and the lower limit depends on the sample size. So we only use Z if the sample size is more or equal to 30. So in my example
so
here,
this is a standard, whatever. So this is not an example now. So
no, this is not an example.
Fixed number.
30 is a fixed number. 30 or above, you can use Z. Less than 30, we use T statistics or student, which exact same as Z, but it's used for small sample. So T statistics is equivalent to Z, but it's used for small sample, and we don't know the standard deviation of the population. That meaning we're using the standard deviation of the sample. So instead, remember we calculated Z as x bar minus mu divided by standard deviation. Now, T is equal to x bar minus mu divided by S, which, if you remember, S is the standard deviation of the sample instead of the standard deviation of the population. So that's the only difference between Z and T. that we're using S instead of sigma. Beside, T is used for small samples, less than 30. This is a fixed number. 30 or above, we use Z. Less than 30, we use students distribution or T distribution.
So the same equation will apply, just changing the
Standard deviation.
the letter instead of S. Yeah.
Yeah, it's not just the letter. It's what the letter represents. The sigma represents the standard deviation of the population. S is the standard deviation of the sample. So if you have both of them, like I could give you an example, I can give you a question in the exam, for example, or in the assignment, giving you both standard deviation. You should know which one to use based on the sample size, if that makes sense.
Yeah, I think it's again needs one example to be more clear about this.
Before moving to the example, there's another thing related to the T statistics, which we call it the degrees of freedom. What degrees of freedom mean? As a calculation, degrees of freedom is equal to the sample size minus 1. So if you have a sample size of 20, the degrees of freedom will be 19. But in general, what's degrees of freedom mean? If I want to give you an example that I have you guys here live with me, 8 students. If I want to take a sample of one person, at the beginning, I have 8 different options. I picked the first student and he left, so I still have 7. I pick another one and he left or she left, then I still have 6 students. So keep on to the last student. The last student, I don't have the freedom to choose. I'm stuck with him or her because it's the last student. So if a sample of 8, your degrees of freedom is 8, which is the sample size, minus 1, that will give you 7 degrees of freedom. Meaning, in the sample size of 8, I have the freedom to choose 7 out of 8 because the last one, which is the last student or the 8th member of the sample, I'm stuck with it. I can't choose anything else.
The point that so this is the point that at which you will not have any probabilities.
Exactly. You don't have any other choice. It's just the last option we have.
Okay.
Why I'm saying all of that? Because when we have small samples, we use T table instead of Z table. T table work very much similar to Z table, but instead of Z value, we use degrees of freedom. So if I tell you in my example that you have a degree of freedom equal to 1 point, let's say 0.1, so the probability here will be 31.82. Exactly same as Z. Remember Z, we used the table to switch between Z value and probability. Now, because I have a small sample,
so this means in the T table here, I'm sorry for the interruption, but this means that here in the T table, the table will have 29 rows, correct?
Exactly. You will have degrees of freedom up to 29. If you look for the entire table, the degree of freedom will be anything between 1 to 29 and the change here, which is 0.1, 0.05, whatever. But will not exceed
so
30.
This is very clear now.
So
and it has a table like the one for the Z value that we can download, huh? I will just
exactly
check
the same
T-table.
thing. You just go to the Google, you search for T-table in any test, in any example. Even if you look at the end of your book, you have that. You have the, if you have the ebook, if you go to the end to the materials, I guess there's a Z table, there's Q table, there's chi-square table, there's Fisher table, there's like multiple tables. But what we're focusing on so far is Z and T. But what I care about here, guys, that you understand that using the T table follow the same idea as Z table. In Z table, I'm switching between Z value and probabilities. Because the value is the sample is small, I can't use Z, so I'm using T. So the T table, I'm using T to switch to probability, or probability to switch to T. T here defined by degree of freedom, which I just explained. Is it clear?
Yes, I just have a question because I looked up in the at Google now. I went through the table. It has till 30, and then the last 5 rows are 40, 60, 80, 100, and 1000. And I think all the tables in the same way.
Exactly. So if you notice, up to 30, they're moving 1 degree at a time. So like you have 1, you have 2, you have 3, you have up to 30. Then they start jumping 40, 50, 60 to 8 to 100 maybe. This is those, everything above 30 is for certain special cases that we don't cover in the curriculum here. So ZT table for you guys is used for small sample that below 30. When you want to use it for a bigger size of samples, let's say 40, 50, 60, maybe up to 100, I believe the table is, that will be for a specific certain situation, mostly related if you don't know the standard deviation of the population. But the common use of the T-table is when you have a small size that is below 30. All right?
Perfect.
Okay, thank you. So now, after we learned about the degree of freedom and the T, using T to build confidence interval is the same idea as using Z. We need the upper limit, the lower limit, and we need the confidence level. So the upper limit and the lower limit is very much the same. X bar, which is the population mean, the sample mean, plus minus T value instead of Z here, multiply by the standard deviation of the sample S by the divided by the square root of n. So exact same formula as Z. What is it? Exact same formula as Z. It's just we're replacing Z with T because we have a smaller size sample. Again, condition to use this, the random should be simple. The sample should be random, and in general, we're assuming normality into the population. So these are the 2 conditions to use student distribution or T distribution. Another example, hopefully this will make it clearer on how we calculate the confidence interval, but this time using T instead of Z. So let's say I have a random sample. The sample size is 25 observation. This sample has a mean of 50. The standard deviation of the sample is equal to 8. What I want to do is to estimate the population mean with a confidence level of 95%. In another word, I want to say that what I want trying to say is the value the value of the mean of the population is 95% rely between lower level and upper level. So I need to find those two. To do so, as we discussed, mu, or the what I'm trying to estimate, rely between x bar minus t multiplied by standard deviation of the sample and x bar plus t multiplied by the standard deviation of the sample. This is the upper limit. This is the lower limit. X bar, I have it, 50. T, I can find it by looking at the table of T. And to find it, I need a degree of freedom. So here I have n equal to 25. So what is my degree of freedom? It's n minus 1. So my degree
24,
of freedom
24.
is 24. Exactly. So now I will go to the table and look for the corresponding value for the 24, and I will find it is equal to 2.064. Then the standard deviation of the sample, I have it 8, and the square root of the population of the sample size is 25. So this is the lower limit. This is the upper limit. Doing the math, I can say for 95% sure that the population mean is fall between 46.7 and 53.3. And this is another example on building
I have a question here, Professor,
yeah.
please.
Go ahead.
Yeah, I'm now trying to apply from the table. So at degree of freedom 24, I have a lot of options that T90, T95, T975, T99, T99.5. All of these options, maybe it's related to more stringent confidence interval, correct? Hello?
Yeah, I'm just looking. I'm trying to find the table on Google. So
Okay.
this is the T table here. If you look at me, guys, if you look with me here. So the first of all, we have the degree of freedom. The degree of freedom here is 24 in my example. So
I think the table is not shared. The table is not shared. I can still see the slides.
All right. Is this better?
Yes.
Yes.
No. Yes.
No or yes? Make it remind.
Now yes.
Okay. So what I'm
Now
trying
it's okay.
to say
Just
is,
need some zoom.
yeah, that I don't think I can help with so much.
It's better if we just save the image and then open it as an image file.
Is this better?
It will be more clear.
Where is it? Come on, man.
This now is okay, doctor.
Can you see this?
Yep.
Yeah, perfect. Perfect.
Okay. Now. So now in my example, can you see the slide now?
Yes.
Okay. In my example, my sample size is 25. That means my degree of freedom is n minus 1. My degree of freedom is 24, correct? So this is the first part.
Okay.
The second part, I have 95% confidence level. That means my alpha is 5, which is 5% I'm mistaken, which we discussed before. Now,
yes,
we go to the table. First, we look for the degree of freedom, which is 24.
24.
So if you look to the line here, you will have multiple values. To pick which value, you look at the first row and you look for your alpha. So my alpha is 0.05, which is 5%. So now 24 and 5%, this is my T, 2.064.
Okay.
Which exactly what I have here in the slide. Clear?
Yes, now it's clear.
Any questions? Okay, so that's how we find T value. Then we put the T value that we found in the table into our lovely equation here to calculate the lower level and the upper level. And my final statement will be that the population, the mean of the population is between 46.7 and 53.3. And that's how you build an interval estimate using T. And before that, we saw how to build that estimate using Z. Same method, same equation to calculate the lower and the upper level. The only difference is if you have a large sample, you use Z. If you have a small sample, you use T.